Hello again everybody and welcome back. In this video we're going to run OpenCV on the Raspberry Pi. So let's take a quick overview look at all the things we're going to do today. We're going to start out with an introduction and then quickly we'll cover Raspberry Pi ESD precautions. Then we're going to jump into making the Raspbian SD card. Then we're going to take a look at the first time Raspberry Pi boot up, and then we're going to take a look at configuring PuTTY and Xming, and those are two utilities that will allow us to program, operate, etc. the Raspberry Pi from our Windows desktop computer. Then we're going to verify that we have a working webcam with the Raspberry Pi. Then we're going to get a LED blinking with the Raspberry Pi. And then we're going to take a quick look at using the Raspbian provided OpenCV precompiled binaries, but we're not actually going to use those. I don't recommend going that route. Instead, we're going to perform an OpenCV compile from source on the Raspberry Pi, and then we're going to quickly run a few OpenCV test programs to test that our OpenCV compile on the Raspberry Pi was successful. Then we're going to look at how to control a servo motor on the Raspberry Pi, and then as sort of a finale project to put it all together, we're going to do a pan and tilt red ball tracker similar to the previous videos, but instead of simply tracking the ball on the screen, we'll have our webcam mounted to a pan and tilt servo, and then the webcam will move around to follow the ball. So that's a lot to do, so let's dive right into it. Okay, so to get started today, let's go to the GitHub site that I've set up for this project. So GitHubMicrocontrollers MORE, and I'll link this in the video description below, but just in case you're wondering how to get there through Google. And then we'll go here and give that just a second to load, and then let's go back to the main screen here, then repositories, and here's what we're looking for: Raspberry Pi 2 and OpenCV tutorial part 1. And let's see, first I should point out that this document here is really the main one we're going to follow during the video today: Raspberry Pi 2 plus OpenCV cheat sheet 3.txt, and if you choose save target as and save it to the desktop, I already saved it there, so I'll just go ahead and overwrite it. Download has completed, and if you do that, what you're going to find is that the formatting looks really odd here. That's not what we're looking for at all. So if you go to raw and then Control A, Control C, and you could read it in the browser, but as you can see, the word wrap here isn't especially friendly. So after Control A, Control C, now we'll paste it in here. And there we go. That's the nice formatting that we're looking for, and you can turn on word wrap here or not once you're in Notepad. So a few other documents we should take a look at here, and the first one's the README. I'll just quickly shoot through all these points here. So this cheat sheet is used to be intended to be used in conjunction with the above linked video, so I'm going to put the video link here when done. Of course, you're already watching the video now, so that's not really necessary, but in any case, the cheat sheet goes with the video and the video goes with the cheat sheet. Neither one is especially intended to stand alone by itself. They're intended to be used in conjunction. So if you're going by the cheat sheet and something isn't clear, please refer to the video and vice versa. During the cheat sheet in the video, I'm kind of assuming some degree of electronics and software knowledge, especially pertaining to OpenCV. And then also you should be comfortable breadboarding a basic circuit and similar electronics fundamentals. So if you're not familiar with those, definitely there are some previous videos on my YouTube channel that you can see for each of those topics. One thing that I will mention at this point is that I'm not going to assume any prior Linux knowledge in this video. I know that that's a tripping point for a lot of people who are interested in electronics, OpenCV, etc., and would like to start using the Raspberry Pi but have never used Linux before, so I'm not going to assume any prior Linux knowledge. This cheat sheet I've differentiated from some of my previous cheat sheets in that I'm using the plain text format that you saw a moment ago, and the reason for that is to facilitate copying and pasting. A lot of what's in the cheat sheet is going to be copied and pasted into a PuTTY session, and if you're not familiar with PuTTY, that's fine, I'll explain it later. But to make the copying and pasting as clean as possible, I've decided to go with a less visually appealing but more functional .text format for this cheat sheet. And the next note here, note 4, so this video and cheat sheet are prepared for the Raspberry Pi 2 Model B+. If you're using a different Raspberry Pi, you may have to adjust some of the instructions. If you're using a Raspberry Pi 1, especially when you get to the computer vision steps at the end, it's probably going to run very slowly. I wouldn't really recommend that, so definitely what I've tested on for the video is the Raspberry Pi 2 Model B+. That's what I'd recommend you use as far as hardware. As far as the operating system on your desktop, I'm recording this video on a Windows 10 computer, and that's what I'm going to go through the steps on today. To my knowledge, all the steps that I'm going to show should work essentially the same with just minor menu differences for Windows 7, 8, and 8.1, but I can't vouch for that firsthand since I haven't tested on those. And if you're a Macintosh or Linux desktop user, everything should work, but of course when you get to the steps where you're interfacing from your desktop machine to the Raspberry Pi, you're going to have to make some adjustments there. And then note 6 here, and this probably some people will be kind of controversial. There'll be some people who are fans of Microsoft a little bit against my decision here, but for the moment I've decided to stick with the Raspbian Linux version as far as an operating system for the Raspberry Pi, despite the fact that Microsoft recently released a version of Windows 10 that runs on the Raspberry Pi. And I've kind of cited various reasons here. I'll leave you to read those separate reasons at your leisure, but really the biggest reason, which I'll mention first here, is that currently the USB webcam support and the official Raspberry Pi camera support for the Windows 10 Raspberry Pi version is essentially non-existent, and that point alone is a showstopper if you're really interested in OpenCV. So for the moment, I'm going to stick and recommend that you stick with the Raspbian Linux distribution for the Raspberry Pi. And then the final note here in the README is that we're going to use Python 2 for all programs today. And the reason for that is that Python 2 is, well, there's really two reasons. One is that Python 2 is the default language for the Raspberry Pi. Everything is set up on the Raspberry Pi to run Python 2 without any additional configuration steps. You can access the GPIO pins without installing anything separate or doing any other configurations. And the second reason is that OpenCV has supported Python 2 for quite some time now, whereas Python 3 support was only very recently introduced. So to some degree there's still some configuration concerns that are being worked through on Python 3, but moreover, you're going to find when you get into a significant project that there are plenty of examples, years and years of examples out there now for Python 2 and OpenCV, whereas Python 3 and OpenCV, you're going to have a very hard time finding examples for that currently. So for those reasons, I am going to, in this video, and recommend that you, at least for the moment, stick with Python 2 when developing on the Raspberry Pi or with OpenCV. And there's just a few more documents here that we should take a look at, and let's see. The first one is a parts list. So as I'm going through the video here, if you're wondering, maybe where I got some of the parts from, here's a list of pretty much all the parts in the video, and for each of them I've cited at least one website, in many cases 2 or 3 websites where you can purchase the applicable parts. And the last thing before we dive into making the Raspbian SD card is, let's see, we should take a look at the Raspberry Pi 2 J8 pinout. So let's see, let's go ahead and download this so we have it on our desktop. So save picture as, and okay, that's good, so we'll go ahead and minimize that. And as you see here, I'm not really much of a fancy graphic artist, but the way I drew this, just to give an idea of the orientation compared to the board, let me pull up an actual picture here of the Raspberry Pi circuit board. Okay, there we go. So this screw hole here is supposed to be this one, and then the activity and power LEDs are supposed to be these 2 LEDs here. So in other words, and this is a little bit different than any microcontroller would be. Typically with a microcontroller, you would start with pin 1 here and then count down 2, 3, 4, etc., and then you count up on the right side, whereas with the Raspberry Pi 2, this is pin 1. So in other words, let me bring this over here a little bit. So in other words, this here is pin 1, and then this is pin 2. This is pin 3, this is pin 4, this is pin 5, this is pin 6, etc. And then if we go all the way to the bottom, then this bottom left pin is pin 39, and this is pin 40. So if you'd like to work with the pins just on the outside, which is how I've set up the circuits today, just to make it as easy as possible, when you're counting, you're going to find yourself counting down here. So this would be pin 2, 4, 6, 8, 10, 12, 14, 16, etc. down the right side. And here I've listed the functions for each of the pins. Some of the pins have shared functions, like for example pin 8 is GPIO pin 14, and then also can be the TXD pin, and then pin 10, for example, is GPIO 15 or can be the RXD pin. So that covers the pinout, and I'll just quickly mention here some information on ESD precautions. I made these 3 videos on how to set up an ESD workstation. That's the best way to work with the Raspberry Pi or any electronics components that are ESD sensitive at all. Realistically, a lot of people don't have an ESD workstation, so if you don't, I would at least recommend following the following precautions. Really, you don't want to work in an area where the floor is carpeted, especially if it's a really fuzzy carpet. If you walk across your carpet and then you touch something metal and you see a spark, or you feel a spark or hear a spark, that's a pretty good indication that you shouldn't handle electronics components on that carpet. Also, a moment before touching the Raspberry Pi, touch a substantial size metal object, so maybe you have a computer case or a metal filing cabinet adjacent to you. Good idea to touch that first before you touch the Raspberry Pi. And then the final thing that I would mention is when handling the Raspberry Pi, if you're not grounded, hold the board by the edges and let your fingers touch only the board edge or maybe the outside of the large connectors, but don't make every effort not to let your fingers touch chips or pins. And then also, before you breadboard a circuit, it's a good idea to shut down the Raspberry Pi with the command sudo shutdown -h now, and then disconnect power, and then breadboard the circuit, and then repower it. Okay, so now that we have the introductory stuff out of the way, we can get to flashing our SD card. So if you type RSPBERY Raspberry Pi, this will take you right to the official Raspberry Pi site. And you're going to want to go to downloads and then Raspbian, and then Wheezy's a little bit older, might as well get the most recent version of Raspbian, which is currently Jessie. So then choose download.zip and then save that to your preferred location. And let's see, the next step is going to be to download and install Windows 32 Disk Imager. So let's see, if we go to help, you can go, just in case you're wondering, you can go directly to it this way, Win32 Disk Imager SourceForge. And that'll take you to the SourceForge page for Win32 Disk Imager. If you're suspicious of a phishing site for that way, or you just rather would see that this is the actual official Raspberry Pi recommendation, let's see, we're under help and then documentation, installation, installing images, writing an image to the SD card, Windows, and sure enough, here's the Raspberry Pi site recommending Win32 Disk Imager, and you can follow their link, and that takes you to the same SourceForge page. And then choose files, and then I believe it's in archive. Yes, it is. And then you want to download this here, or whatever the most recent version is as of when you're watching this. Most computers today are going to have an SD card slot. If yours doesn't, you can purchase an SD card reader. For example, you can find one on Amazon.com pretty quickly, like this one. Connects via USB, but again, that's probably not even necessary. Most desktop computers today have a SD card reader. Okay, so once you've downloaded and unzipped the most recent version of Raspbian, and you have downloaded and installed Windows 32 Disk Imager, I think I forgot to mention all the default choices are fine for Windows 32 Disk Imager during the install. Then you're going to want to go ahead and insert your SD card. And in case you're wondering, for those of you new to the Raspberry Pi, the Raspberry Pi actually takes a micro SD card. So if you purchase either of the SD cards I mentioned in the parts list, that's going to have the micro SD card and then an adapter to a regular size SD card. So go ahead and put the micro into the adapter, then insert the adapter into your computer, and then you should get a pop-up, and there we go. So let's see here, and I recommend at least a 16 gigabyte SD card. You don't really need any bigger than that. So the first thing you're going to want to do is format. So I should mention actually to make sure you have which drive letter your SD card is straight, because you're going to be formatting it, so you obviously don't want to format the wrong thing. So if you pull up your file browser here and then insert your SD card, whichever one appears, of course, is your SD card. So there we go. Now we know for sure that this is our SD card. So then you're going to want to right click on that and choose format, and you can erase any volume label that's there. That doesn't really matter. I always like to choose restore device defaults, and then you can go ahead and choose start. Warning, this will erase all data. Yes, of course we know that. Format is complete. And then we can close this format window. And then we're going to fire up Windows 32 Disk Imager, and it asks for administrative access. Yes, of course we want to grant it that. And then you're going to choose this here to browse to your Raspbian download location. And so this is what you want to choose, Raspbian Jessie or whatever the most recent version of Raspbian is that you downloaded. And then make absolutely certain that you have the device drive letter chosen for your SD card. And then choose write, and it's going to warn you that that's going to erase everything on the SD card. etc. Are you sure you want to continue? Make absolutely certain you have the drive letter chosen correctly, and then choose yes. And it takes maybe 5 to 10 minutes to write Raspbian into the SD card, so I'm going to go ahead and pause the video for a moment. Okay, so Windows 32 Disk Imager just finished writing Raspbian to the SD card, so we get this pop-up here, write successful, and then we can choose OK and then exit out of Windows 32 Disk Imager. The next step is to right-click on the drive letter for your SD card, and eject may or may not be an option here. And the reason for that is, let's see, if we go to Properties, and it always takes me a minute to find this setting. I think it's under, Hardware. There we go, Disk Drives, and then Properties, and then I believe it's Change Settings, and then Policies. There we go. Depending on if you have write caching enabled or not, that determines if eject is an option. So in other words, when you choose to write to an SD card, it might not actually write to it until you eject it, if you have write caching enabled. So to make a long story short, right-click on your SD card. If eject is an option, go ahead and choose eject, and then remove the SD card. If eject isn't an option, then you don't have to worry about it. You can just directly remove the SD card. So in my case, eject is an option, so I'll choose that first. Then the SD card disappears. Now I can go ahead and remove it. And let's take a quick look at the cheat sheet before we go over to the electronics bench. So in this next step, what we're going to do here is we're going to connect the USB keyboard, mouse, wireless adapter, USB webcam, and HDMI monitor cable to your Raspberry Pi, and then make sure you have the SD card inserted at that point, and then you can connect power. You usually want to connect power last. There's no actual on switch on the Raspberry Pi, so whenever you connect power, it turns on. And then we're going to do these steps on the bench, so I'll go ahead and pause the screen recording. Okay, so we're back over here at the bench. So we've got the USB mouse, keyboard, wireless adapter, and USB webcam connected, and the HDMI monitor. So we'll go ahead and take the micro SD card out of the adapter, and there's one I was working with previously. We'll start with the one we just flashed. So then we're going to go ahead and insert it like that. And now before I connect power, I'm going to stop the recording for just a moment to reposition the camera. Okay, so I'm going to go ahead and connect power to the Raspberry Pi. And now it's going to perform its first boot. And the Raspberry Pi Foundation did significantly change this recently. It used to be that upon a first boot up, the Raspberry Pi by default would boot to a command line and not log you in. Now it automatically logs you in as user Pi and password Raspberry, and boots you directly into the graphical desktop. So I'm going to show you here how to change that for two reasons. One, you could be comfortable with it if you ever need to boot into a non-graphical environment, and for two, we're going to use PuTTY and Xming from a Windows desktop for pretty much the rest of the tutorial, so you won't even need to boot into a graphical desktop, and it's better not to have the Raspberry Pi spend the computing time on rendering the desktop since we won't be using it anyhow. So first we'll bring up a command line here, and let's go ahead and resize that. And then we're going to type, there's something I should mention first here. If I hold Shift and then type an @ symbol, actually let me make this font way bigger here, hopefully that'll make it show up better on screen. So let's see, edit preferences, and I'll make this really enormous. Let's make it 14, and there we go. Okay, hopefully that's viewable on screen. Just another moment while I resize this here. And okay, that should work. Alrighty, so if I hold Shift and press 2, you would expect to get an @ and currently we get a quote. And if I hold Shift and press quote, we actually get an @ obviously that could cause a lot of problem with a programming language, so we're going to fix that as well as some other things by typing sudo, which is short for super user do, in other words root access, RASPI-CONFIG, and that's going to bring up Raspbian config. And we're going to change three things here. We're going to change option 1, expand file system, so just press enter, and then it's going to, the root partition has been resized, the file system will be enlarged upon the next reboot. So that's going to make all the space on our SD card usable now. And then the next thing we're going to go change is we're going to go to boot options, and then we're going to change that to B1 console. And when we get to using PuTTY and Xming, it'll make sense why we don't want to bring up the graphical desktop by default. Later on, if it doesn't make sense already, press enter there. And then to fix that keyboard concern I showed just a moment ago, that's because the default keyboard is set for the United Kingdom. So we're going to press enter on 4 internationalization options, then we're going to go down to keyboard layout and give it just a moment to process. And when it comes up, you can choose a fancy keyboard if you have one. I'm just going to choose the generic 105 key Intel PC, and then you'll notice these are all UK, so you want to go down here to other, and then you'll notice UK is the default, so we're going to want to go down to US. There we go. And then if you have a particularly fancy or specialty keyboard, you can choose it, but I'll just choose the general US one. Obviously, if you have a UK keyboard, leave it as a default. If you have a different country, choose your country. But I'll choose US, and from this point you can just choose the default. So enter, enter, and enter, and you can set some more configurations in Raspberry Config anytime that you prefer, but that's all we really need to do. So I'm going to press tab twice and go to finish, and then enter. It's going to ask me, would you like to reboot? Yes, let's go ahead and reboot. And then while we're waiting for the reboot here, I'm just following along in the cheat sheet, make sure I didn't miss any steps. Okay, so the next thing that we're going to do is we're going to log in with the default username and password, which are username Pi and password Raspberry, all lowercase. And then we're going to type start X to start the graphical desktop, and then we're going to set our IP address. And then at that point we're going to shut down the Raspberry Pi, go back over to the desktop, and use PuTTY to SSH into the Raspberry Pi. If that doesn't make sense, it will a little bit later. So Pi, and then password RASPBERRY, all lowercase, and then STARTX to start the graphical desktop. And that'll come up in just a minute, and what we're going to do is we're going to choose this wireless icon towards the upper right here. Let's give it just a moment to render. And again, I'm not sure how well this is going to show up on the recording, so I'm sort of trying to narrate what I'm doing as well. So at this point what you're going to do is you're going to choose your wireless router, and then on the next screen you type in your wireless router passkey. It's pretty intuitive. Obviously I'd rather people don't know which is my wireless router and which is the passkey, so I'm going to stop the recording for just a second while I do that. Okay, so continuing on, I just entered my wireless router passkey, and I don't know how well this shows up on screen. Maybe I'll zoom in a little bit, but the icon towards the top, as you can see, turned into an emitting wireless symbol, so we know that that's working. So now I'll zoom back out again, and we're going to bring up a command line again. So go back up here, and let's see. The next thing we're going to do, actually the last thing that we have to do at this point, is we need to find out our IP address. It is possible to address the Raspberry Pi by hostname, but there's additional configuration steps involved. The easiest way to do it is by IP address, so that's how we'll do it today. So HOSTNAME space dash uppercase I, and what you'll want to do is the IP address at the beginning there. So in my case 192.168.1.71, you'll want to write that down, and then we want to shut down the Raspberry Pi with the following command: sudo shutdown SHUTDOWN -H for halt, in other words, meaning don't reboot, and then now for the time. You have to specify a time, and let's go ahead and press enter. And once you see the screen shut off and the read-write SD card access LED on the Raspberry Pi, which is labeled ACT for activity, once that stops blinking, the boot down is complete, so we can go ahead and unplug power from the Raspberry Pi and then connect it back in, and it's going to boot right into the login prompt, and we don't have to do anything further. And I'm going to go back to the desktop to continue the screen recording there and explain the next steps. Okay, so back to the desktop screen recording. So after performing the shutdown, which I showed just a moment ago, the next thing that you want to do is reconnect power to the Raspberry Pi, and how we reconfigured it. It will boot to a command line login prompt, so it won't auto log you in, and there won't be a graphical desktop. So the question now is, how do we connect to the Raspberry Pi from our Windows desktop? And that's what we're going to cover in this section here, PuTTY and Xming. So the first thing that you want to do is install PuTTY. So you can go to this location here, and we'll paste that in. There we go. And what you want to download is this right here, putty.exe. If you're suspicious of filtering sites, or you'd rather go RASPBERRY, Raspberry Pi, you'd rather go directly from the official Raspberry Pi site, there is a link on there to the same location. I believe if we go to help, documentation, I think it's remote access, SSH, Windows, and if we choose this link, I believe that, yep, goes exactly the same page. So what you want to do is download PuTTY.exe. That's actually an executable. There's no separate installer for it. So what you want to do is on your C drive, you want to make a directory named PuTTY or similar, and then you can just download PuTTY.exe to there, and then right click on that, do send to desktop, create a shortcut, and then you'll have a shortcut to PuTTY on your desktop. So the next step is to install Xming and Xming fonts. So let's see, if we type Xming SourceForge, that should take us right to it. And let's see, we're going to want to install Xming first and then Xming fonts. So Xming and then the most recent version, so you'd want to go ahead and install this. And then once that's complete, you would want to go to fonts, and then you want to install the most recent fonts. And I should just quickly mention here in the cheat sheet, so when installing Xming and Xming fonts, you can choose all the defaults except for the following options. When you're installing Xming, I'd recommend to create a shortcut on your desktop to Xming. And then also when you're installing fonts, it gives you an option. It doesn't select all of them by default, but it gives you the option to select all of them, so I'd recommend just go ahead and install all fonts. Another thing is when you're installing Xming fonts, it may give you this warning here. The Xming directory already exists. You want to install Xming fonts to the same directory. If that appears, go ahead and choose yes. And then after you've installed PuTTY, Xming, and Xming fonts, go ahead and reboot. And then we can start PuTTY. So we'll go ahead and fire up PuTTY here. And just a moment while I resize the cheat sheet in the other window. Okay, there we go. So when you open PuTTY, it's going to look like this. So what you're going to want to do, and I'll delete this my default here and then remake it just to show you how to operate PuTTY here. Okay, let's get out of that. Okay, so there are some settings that we're going to want to choose. So the first is you want to enter your IP address. So as you saw, for example, mine is 192.168.171, and that was where we did the hostname -I command on the Raspberry Pi. And then the next thing you're going to want to go to, if you don't want to hear a whole lot of dinging sounds, is you're going to want to go to terminal and then bell, and then action to happen when a bell occurs. I'd recommend choose none. And then you're going to want to go to connection, and then this seconds between keep alives, you're going to want to set that to 30, and that will prevent your PuTTY session from timing out. It sends a dummy packet every so often, just enough so that the connection remains. And then you're going to want to go to, let's see, connection, and you're going to want to expand SSH and then choose X11, and then you're going to want to check the enable X11 forwarding box. And then you're going to want to go up here back to session, and then you're going to want to save the session. So for example, you could call that my default and then save. So now if we exit PuTTY and we go back in and we choose my default and then load, so it reloads our IP address, and then it should have saved all our other settings too. So there's bell, there's connection, and there's SSH. Okay, good. So we got that working for us. So now all we have to do is jump into PuTTY and then choose my default and load and open, and that will, it always gives you this warning the first time that you're connecting to a Raspberry Pi after having flashed the SD card. As long as you're sure the IP address is correct, which we are, then we can go ahead and choose yes. And now we're to the login prompt, just as though we were sitting in front of the Raspberry Pi. So I'm going to type pi and then password, all lowercase, RASPBERRY. And then something else that I forgot to mention is, let's see, continuing on with the cheat sheet here. What you want to do is, this here is just a shortcut to Xming. So if you have Xming on your desktop here, you can right click on here and then choose pin to taskbar. In my case it says unpin to taskbar because it's already there. But you'll notice in the system tray, also known as the notification area down here, there's no Xming. So what you want to do is you can start Xming either from the desktop or if it's pinned to the taskbar, either one. And you'll notice this just appeared. So you got that black X with the red sort of half circle around it. That means Xming is running. And what Xming does is it via X forwarding renders Windows from a remote Linux computer, in this case the Raspberry Pi, onto a Windows desktop. So let's go ahead and test PuTTY and Xming now that we have Xming going. So by the way, to copy and paste into a PuTTY window, You don't even have to press Control V. All you do is, I'll just show you that I'm highlighting here. So I just highlighted PWD in the cheat sheet. So now I'll move that back, and if you just right click anywhere in the PuTTY window, it automatically pastes. And then if you press enter, there you're doing your Linux command. So PWD is short for present working directory. So in other words, that's letting us know that we're currently in the home directory and then the pi directory. For those that are new to Linux, if you do cd and then / that takes you to the root directory. There aren't drive letters in Linux like there are. Windows has, C, D, E, etc. different drives. Linux just has one master location, which is root, which is just a single /, and then these are all the directories in root. So where the user accounts are is if you go to cd and then home. This is, and then ls is list of files, and -l puts one per line with some additional information. So that's going to list all the user directories. In this case, we didn't make any more user directories, so there's only the one pi user. So if we type cd pi, that'll put us into that directory, and there's what's there by default. In case you're in another directory, like we'll go back to root, if you ever go cd and then tilde, that takes you to the home directory for the current user. So we just did cd tilde, and you'll notice there's this tilde in the command line here that's reminding you that you're at the home directory, or you can do pwd and see that you're there. Okay, so let's do a few more Linux commands here to test our PuTTY sessions working okay. So list, we already did that. And then now let's test X forwarding. So if we do PCMan FM and then an ampersand, starts programs as a separate process or forks them as a separate process in Linux parlance. And what PCMan FM is that's the file browser in Raspbian. So that 1897 at the bottom of the screen there, that's the process ID for the process we just started, and here is our window. So this is a window that's being rendered by the Raspberry Pi onto our Linux desktop, and we can navigate files there. And then just as one more example, for most programs from the Linux command line, you can press Control-C to exit. So we'll go ahead and paste in Epiphany browser ampersand, and that's the file browser on the Raspberry Pi, the default file browser on the Raspberry Pi, and it takes a moment to start up again because the Raspberry Pi is rendering these windows and then sending them via X forwarding over to our Windows desktop. There's a substantial lag, but as you can see, it does work. So if we go www.google.com, that should go ahead and bring up Google. And sure enough, it does, or it's going to. So while we're waiting for that, most of the rest of the cheat sheet, or a lot of the rest of the cheat sheet, is simply copying and pasting commands from the cheat sheet into PuTTY. And another thing I should mention is if you ever want to copy from, I just showed how to paste into PuTTY, that you just right click in the PuTTY window. If you ever want to copy from the PuTTY window, you just highlight what you want to copy. You don't have to even press Control-C. It automatically copies it. So then if we bring anything up we can paste into, for example, Notepad, now if I do Control-V, it's going to paste in what we had just highlighted in the PuTTY window. So you don't have to use Control-C, Control-V in the PuTTY window. It automatically copies and pastes for you. Just highlight stuff to copy it or right-click to paste it. And as you can see, our browser has come up. So and again, this is the Raspberry Pi rendering this browser window. So everything's working for us. Control-C. So we have successfully gotten PuTTY and X forwarding working for us. So the next step we're going to do, we might as well just dive right into the next section here. So next we're going to verify that our webcam works. So bear with me for just a moment here while I resize the cheat sheet in the other window. Okay, so if you use the ls USB command, that lists all connected USB devices. So for example, the webcam that I have connected currently is the Logitech HD Pro Webcam C920. Yours may be different. Hopefully yours is visible. And sometimes on the screen, depending on the webcam, it might just have a list of numbers, or the name might not especially be clear. So another way that we can check is we can cd to the dev directory as follows. So cd dev, and then we can list. And the dev directory is, as I mentioned earlier, Linux doesn't really have sort of a separate hardware manager equivalent how Windows does. So what they do is in the dev directory, this is where all the devices are listed, and they at first glance maybe look like files, but they're actually devices. So what we want to do is we want to look right here for video 0. That's our webcam. So we're all set there, and then we can, as I mentioned earlier, to return to the home directory, you can just cd tilde. And now we're going to install fs webcam with the following command: sudo apt-get install FS Webcam, I'll explain this quickly. Sudo is super user do, so that's root access or administrative access. apt-get is the package manager which Raspbian uses, which is based on the Debian distribution, which is one of the oldest and most common Linux distributions. In fact, essentially, you could say that Raspbian is a custom version of the Debian distribution specifically for the Raspberry Pi hardware, essentially. And then install, of course, is the command for apt-get to install, and then FS Webcam is what we're installing. So we're going to go ahead and install, and when you install with sudo apt-get, if the file is even a relatively significant size that you're installing, or the program I should say, it will say this is going to take up a certain amount of disk space, are you sure you want to continue? And you're going to see that a lot throughout the rest of this tutorial, and then it'll have an uppercase Y and a lowercase n, so that means that yes is the default. So when you see that, you can just press enter and it'll go ahead and install it. FS Webcam is such a small program, it may not even ask us that. In fact, I don't think that it will. And once it's done installing FS Webcam, which will probably take just another moment, then we're going to go ahead and take a picture with our webcam to test it. What I'm planning on doing is once I start something installing, then I'm going to go ahead and pause the recording while it's installing, because there's no sense to just kill time in the video having the installations go on and on. So if my installations are taking 10 seconds each and yours are taking 5 or 10 minutes, that doesn't mean you're doing anything wrong or that anything's wrong at all. It's just that I'm fast forwarding while things are installing. So let's see, it looks like it's almost done here, setting up FS Webcam. And then, okay, so here we go. So FS Webcam -R is short for resolution, 640 by 480, so we'll use that resolution. And then the -- banner at the bottom here, that's going to prevent it. If you don't put that flag in, FS Webcam puts kind of an odd-looking banner, which we don't really need. And then image.jpg is going to be what we're going to name our image. So we'll go ahead and take the image from our webcam that way, and now we're going to list it. And sure enough, there's image.jpg right there for us. And we can even view that if we like with PCMan-FM. So again, that's the file browser, and there it is. And if we double-click on it, it will appear. And there's a scene in my apartment, nothing especially exciting, but our camera did work, our webcam worked. So now we're going to install LUVC, whoops, okay, forgot to do Control-C there. Now we're going to install LUVC view. And this is similar to FS Webcam, but it's for streaming video instead of still images. So we're just going to check and make sure that we can get streaming video from our webcam before we continue. And now we're going to execute the command LUVC view -S is for size, 320 by 240. So I'm going to put down my headset for just a moment and wave my hand in front of the camera just to prove it's live. And there was my hand very quickly waving. As you notice, there's a very substantial lag because of the X forwarding, but as you see, it did work. And so now we're going to jump back over to the electronics workbench, and we're going to do this next section, get a LED blinking. Actually, before we do that, the first step in get a LED blinking is to breadboard myblink.png, so let's take a quick look at that. So you probably recognize this page by now, so let's see, myblink.png, and we can go ahead and view the raw. So I put this notch here in this note just to give you an idea of the pin orientation, but as I mentioned earlier with the Raspberry Pi 2 J8 connector, that's the 40 pins on the corner of the board. The easiest way to do it is if you start counting up here at pin 2, 4, 6 down, etc. until you get to pin 12 and pin 20. So this is our circuit here. So on pin 12 we're going to have a LED, and then we're going to have a 470 ohm resistor, and then we're going to connect that to pin 20 for ground. So let's go ahead and stop the screen recording and jump over to the electronics bench. Okay, so this is a pretty simple circuit to breadboard. So all we need to do here is we need to connect a jumper wire to pin 12. So we'll go ahead and do that. So just count down the right side here. So that'll be pins 2, 4, 6, 8, 10, and then 12. And then we're going to connect that onto our breadboard. And then this is a series circuit, so it doesn't matter if you do the 470 ohm resistor next or the LED. I'll just choose to do the LED. So make sure you get your LED the right way around. With most LEDs, the part that appears to be smaller on the inside is the side that goes to power. So we'll go ahead and connect that up like that. And then we're going to go ahead and connect up our 470 ohm resistor as follows. Let me get that in there. There we go. and then we're going to connect our other jumper wire to the ground side of that, and then to pin 20, so we're on pin 12 now, so 14, 16, 18, and 20, and that's it. And let's go back over to our desktop. Okay, so back to the desktop screen recording here. So continuing along with the cheat sheet, we just breadboarded my blink.png, and so if you're wondering about that 470 ohm resistor value, that's this line here. What you want to do is take a look at this document, resistor for lead calculation.pdf. Let's just take a super quick look at that. I'm not going to get lost in the theory for too long here. Let's see, resistor for lead calculation.pdf. Okay, so here's what I'll save it to the desktop. It looks a little better there. We can view it full size, save as, desktop. Okay, download's completed. Let's go ahead and open it, minimize everything. And I'm going to drag the PDF viewer over here, make it maybe just a little bit bigger, 115. Okay, that sounds good. Okay, so suppose we have the following circuit. So this is the actual circuit we have, of course. So the question is, how much resistor value do we use? So if we look at this next diagram here, here's some approximations. So the Raspberry Pi's GPIO pins, if you use them as source, in other words, for high side drive, they're going to output 3.3 volts. So if we take a typical silicon PN junction, we're going to get, for example, in lead, you're going to get a drop of anywhere from, say, 0.6 to 0.7 volts. So to average that out, let's just say 0.65 volts drop across the lead. And then, of course, as we mentioned, the Raspberry Pi GPIO pin is going to give us 3.3 volts. So 3.3 minus a 0.65 drop means after the lead we're going to have 0.265 volts. So the question is, how much do we make the resistor? Well, the voltage drop across the resistor is going to be 2.65 volts. So we can calculate from that, and by the way, there's some rules of thumb here. The GPIO pin should not be used to source more than 16 this is for the Raspberry Pi specifically, of course, more than 16 milliamps per pin and never more than 50 milliamps total. And really, you shouldn't even get close to that 16 milliamps per pin rather. So that leaves us with the following calculations. Of course, voltage equals current times resistance, as we know. So if we were to take this 2.65 voltage drop that we've calculated as occurring across the resistor, so 2.65 divided by, let's say, 470 ohms gives us 0.0056 amps or 5.6 milliamps. Remember, we have to, per pin, absolutely always stay below 16 milliamps, and we can't go above 50 milliamps total for all the pins. So 5.6 milliamps is okay. Let's say we used a little bit lower value of a resistor, 330 ohms. Of course, the lead's going to appear slightly brighter, and that's going to be 8 milliamps. If we were to use an 1000 ohm resistor, then that would be 2.6 milliamps. The lead would appear really dim, though. It might even be difficult to see. So to make a long story short, any of these three values is acceptable. 470 ohms is kind of a nice value to use that's going to very comfortably protect the Raspberry Pi's GPIO pins from overcurrent, but at the same time it's still going to provide enough lead brightness. I really wouldn't recommend using anything less than 330 ohms. I've seen some Raspberry Pi beginning blink tutorials that recommend as low as 100 ohms. That's a really bad idea. You could damage the pins on the Raspberry Pi over time doing that. So 1000 ohms, yeah, that'll work, but you might not be able to see the lead. So 470 ohms or thereabouts, I really don't recommend any less than 330 ohms, and then you should be all set. Okay, so let's get back to where we were. Okay, so Raspberry Pi JAD pinout. Okay, so we already checked the pinout. So now continuing at the command line, so we're going to go back to our PuTTY session here. Okay, so we're going to cd tilde to make sure we're in the home directory, which we already were. And then when you create a file, or to create a file, I should say, in Linux, if you'd like to create a blank file, you can type nano and then the name of the file. And if it doesn't exist, nano is a very common editor, by the way, for in Raspbian. If you type nano and then the name of the file, and the file doesn't exist, it'll create the file for you once you save it. Or alternatively, you can use the touch command. By the way, in Linux, if you type man, that's short for manual, and then touch, it tells you what a command does, gives you some of the option flags, etc. So touch is to update the access modification times of each file. It has more particular uses, but one use you can use for touch is to make files that are blank. So if you type touch and then myblank.py, and then we do another list, then myblank.py is there now and it's empty. So you can use the touch command to make an empty file, or you can just specify the file name in Nano, and then when you save it, Nano will make the file for you either way, whichever you prefer. So in this case, I just chose to make the file first, a blank file first with touch, because that, generally speaking, is my preference. So then we'll go ahead and open it in Nano. And then we're going to go back to, of course, I'm sure you recognize this page by now, so we're going to go to myblink.py, and then raw, and then Control A, Control C. And then we're going to paste that in there. And let's just take a quick look at this program. So GPIO.setMode, you can use a GPIO.bcm or GPIO.board. So let me explain that. Referring back to the pinout, let's see, pinout. So for example, we're using pin 12 or GPIO 18. So if we were to, well, let's first take what we did. Since we use GPIO.bcm, we're going to refer to that pin as 18 because we used BCM, meaning Broadcom, the chip. So in other words, that uses the GPIO numbers. Whereas if we used board here, then we would refer to our pin by the physical pin number. So then we would use 12. So in other words, if we used board here, this would be 12 instead of 18. Generally speaking, it's cleaner to use the Broadcom GPIO numbers for pins rather than the physical pin number. So that's what we'll do here. So GPIO.bcm specifies us to use the GPIO pin numbering, not the physical pin numbering. And then the LED pin, of course, as we saw from here, or going back to the schematic that we just breadboarded, let's see, myblink.png, pin GPIO 18 or physical pin 12, of course, is the pin for the LED. So since we're using the GPIO pin numbering, we're going to have this variable LED GPIO pin is assigned 18. And then we call this setup function here, GPIO.setup. So then we feed it in. You could enter the number 18 here, but it's cleaner to assign the 18 to a variable name and then just reuse the variable name. It makes the program more readable. So you pass in which pin that is, and then GPIO.out specifies we're going to be using that as an output pin. Of course, that's a high side drive for the LED. So then we're going to have our infinite loop here while true, and so the user will just press Control C to exit the program. So then GPIO output, so here we're going to set the LED high, so GPIO LED pin and then GPIO high, and then we're going to wait for a half second, and then of course we're going to set it low, as you probably guessed, and then we're going to wait for a half second, and that's going to infinitely loop. So in the Nano editor, to save a file, you simply type Control or press Control O, and it says down here write out, that means save. So Control O, file name to write, myblink.py. Yes, we'd like to save it as that, so press enter and then press Control X to exit. And I'm going to stop the recording for just a second to set up picture-in-picture. Okay, so I haven't used picture-in-picture in a tutorial before. Hopefully this will be helpful to see the LED blinking. So now that we've entered our program, we're going to paste in sudo python and then myblink.py, and it is necessary to put sudo there at the beginning because you need root access anytime you're accessing the GPIO pins on the Raspberry Pi, otherwise you'll get a permission error. And as I turn around, I can see the LED blinking, and hopefully you can see it on the picture-in-picture. And so we've successfully got a LED blinking. Okay, so I had to pause the recording there for just a second to make sure I had the picture-in-picture working. So continuing on here on the cheat sheet. By the way, with the Linux command line, if you ever want to clear the screen, you simply type clear, and then that takes you back up to that. So sometimes that can be helpful if you have a whole lot you're not trying to see. Okay, so continuing on with the cheat sheet here. Let's see, we just got a LED blinking, so that was this line here. Okay, so this part here, which we'll just shoot through quickly, covers if you would like to use the Raspberry Pi in an embedded application where you would not have to type something or press a button or something to that effect to make it start doing something. So as soon as you connected the power up, so if you made this the brains to a robot or something, and you wanted to make it so as soon as you turn the power on, it immediately started running its program, here's how you would do that. So the first thing that we're going to do is we're going to edit this file here at set and then RC local. We're going to add a line just after this if and before exit. So I'm going to that didn't work, just a moment. Okay, there we go, right click. So that's what I was trying to do. So sudo python, and then you have to give it the entire location of your program. Of course, we were in the home directory before, so we didn't have to do that since that's where the program was, but here we have to specify home pi and then myblink.py. And You can put sudo at the beginning here or not. It actually doesn't matter because this file, it's set rclocal, is ran as root during the boot up process anyhow, but it doesn't seem to hurt to leave sudo in there. And then something that I definitely should mention is this ampersand at the end. That's critical because if your program has an infinite loop in it, for example, how this one does, the Raspberry Pi may continually run that program and not complete the boot up process. So you definitely want to put the ampersand in there to fork your program off as a separate process. So if there's a problem with your program, or if it has a purposeful infinite loop in it, or for whatever reason it goes on infinitely, that the Raspberry Pi will finish booting, and then you can fix the concern and continue from there rather than have it hang the boot up process. So at this point we're all set. So now we can do Control O to write out and then Control X to exit. And then we're going to go ahead and do a reboot, and the command for that is sudo shutdown -r now. And of course we lost our connection as soon as we rebooted. And I'll go ahead and re-log in, but really what we're looking at here is the picture-in-picture. The LED should start blinking in just a moment, and I can see from my extra computer screen that the Raspberry Pi reboot is almost done, and there we go, it just finished, and now the LED's blinking. So that did work. So now we'll go ahead and return it to it not running that program. So let's see, my default load, and then we'll open, and then that'll bring us back to here. So Pi, Raspberry. By the way, if you ever want to change the password, you can do it from the graphical environment, or you can simply type pass WD, and then if I recall, it asks you to type in the old password and then a new password twice. If you're using wireless networking, that's probably not a bad idea. But in any case, let's restore that exec rclocal file. So we're simply going to scroll down here and delete this, and then Control O, Control X, and now we can reboot again, and then it will not run the program for us. So of course we lose our connection anytime we do that, and I'm going to go ahead and stop the recording for just a moment. Okay, so we've completed the LED blinking section, and now we're on to the using the Raspbian provided OpenCV precompiled binaries section. In this section we're not actually going to do anything, but I'm just going to show you why I think it's not a good idea to use the precompiled binary. So if you let's go ahead and bring up another session here. So my default load, open, and then Pi, Raspberry, and then if we execute the following command here, dpackage -L, L is for list, and then pipe character and then less. And what this is going to do is it's going to send the output of the dpackage command to the program less, which allows us to scroll up and down. So in less you can use up and down keys to scroll like that, one line at a time, or you can press page up and down to jump around pages. And what the dpackage -L command is this list with additional information for each package, everything that we have installed currently. So if we go down to, I believe it's OpenCV, or live OpenCV rather, there we go. So here are the OpenCV libraries that are installed with Raspbian by default as a version Jesse. And this is 2.4.9, which I believe is about a year and a half old. OpenCV changelog, CHANGE, there we go. And if we search for, I think it's here on the right, yeah, there we go, 2.4.9. So April of 2014, so almost a year and a half old now. You could use these, it wouldn't be the end of the world. If you were to use the OpenCV precompiled binaries, it's actually very straightforward. Here's how you do it. You would first do sudo apt-get update, sudo apt-get upgrade, and then this simple command here, which is going to install OpenCV dev and then Python OpenCV, and then at that point, to verify your OpenCV install, you could simply do Python to bring up the Python interactive prompt, which is what these three dashes indicate, and then you could do import CV2 and then CV2 version, and then it would say 2. I have to update this because with the previous version it was 2.4.1. That's now should say 2.4.9 is the version you get, as you see here from the precompiled binaries from the dpackage command. I really don't recommend that, though. However, to use the precompiled binaries, it will save you the compile time. But there have been substantial changes to the Python syntax from version 2 to version 3, and I'd really rather not go back to version 2 at this point. When I say version 2 to version 3, I mean OpenCV version 2 to OpenCV version 3, pertaining to Python 2 specifically. Continuing forward in the rest of this tutorial, any of the Python programs that use OpenCV won't actually fully run with OpenCV 2.4.9 or OpenCV 2. Anything, because the syntax was slightly different, and it's really not a good thing to go backwards at this time. So honestly, I don't recommend that. So let's dive into this next section here. OpenCV compilation, and I should mention ahead of time, this takes about 3.5 hours total on a Raspberry Pi 2, and this one command alone here, sudo make, takes about 3 hours. So you don't have to really watch the computer for most of the time, only maybe a half hour of it, if that. And I'm going to fast forward through the install steps, so it's, of course, in this video it's going to appear to move faster than it actually does. But other than this step where you're waiting for 3 hours, it really doesn't take that long, maybe half an hour, otherwise probably not even that much. And you can just let it compile overnight or when you're out doing something else for a while, and then this way you'll be at OpenCV. Currently we're at OpenCV 3.0.0, so if you're doing this even after that, you'll get a newer version of OpenCV, but the point is it's better for consistency to be at least OpenCV version 3. So let's go ahead and dive right into the compile and see. Just a moment here, I'm moving the cheat sheet around in my other screen. Okay, so to get started, we're going to make sure we're in the home directory, which we already are, and then we're going to do sudo apt-get update, and that shouldn't take more than a minute. Of course, Raspbian Jesse just came out, so there's the update and upgrade commands aren't going to have a whole lot of changes to include. Once a Raspbian distribution has been out for quite some time, they seem to come out about every 4 or 5 months. They'll make an update to it. That is to say, the Raspbian organization will change the version of Raspbian entirely. If you're doing the apt-get update and upgrade commands towards the end of that time, of course it's going to take longer to do those because there'll have been more updates since the last major release. But in this case it should go pretty quickly. Okay, so update just finished, so now we're going to go ahead and do sudo apt-get upgrade. Okay, so apt-get upgrade just finished, so now we're going to go ahead and install Python NumPy, Python SciPy, and Matplotlib. You might never use SciPy and Matplotlib, but might as well go ahead and install them now and include them in the compile just in case you need them later. And when you get this prompt here, it says, do you want to continue? We'll take some amount of disk space. You'll notice that the Y is uppercase and the N is lowercase, so that means that yes is the default, so you can just press enter here. Okay, so those Python installs just completed. For those of you that are new to using the command line, if you're wondering, if you press up, that tells you what your last command was. So there's the one we just did, and then up tells you the one before that and the one before that, and then down takes you forward up to a blank line, meaning the current command. So in other words, if you stepped away from the computer for 5 or 10 minutes and you're wondering what step did I do last, just press up once and see, oh, okay, we did the Python installs. So now we're ready to install build essential, CMake, and package config, and I believe Raspbian now includes. Yes, we want to continue. It does include build essential and package config, so this is only actually installing CMake, so this will be pretty quick. Okay, so next we're going to install the default Java Development Kit and Ant. Okay, so the JDK and Ant just finished installing, so now we're going to install libgtk gl extension 1. Okay, so libgtk gl extension 1 dev just finished, so now we're going to install Video for Linux Utils. I'm pretty sure that Raspbian includes this now, so it should already be at the newest version. Yes, it is, but I still suggest doing that line just in case, because that's critical for the OpenCV compile. And now this next line, in case you're wondering, by the way, I'll drag it over from the other window here. I'm just copying and pasting, working my way down the cheat sheet. So this next command includes a number of programs here. Some are for video codec, some are for still image codec. Others serve different purposes. Of all the commands so far, this is the one that I really have the least ability to future-proof as far as these instructions working, say, a year or 2 years from now. And the reason, of course, for that is that I don't have any knowledge or control over how Debian might change in the next 2 years, Raspbian, OpenCV, any of these software utilities in particular that we're using. So if you're watching this video, say, a year from now or 2 years from now, and you go to execute this command and you get an error, generally speaking, the command line is at least relatively friendly as far as the error messages it gives you. So, for example, it might say, lib v41-0 is now out of date, but lib 41, or rather 42-0 or 41-1 is available, or some other error message that hopefully is relatively intuitive. If it gives you an error message like that, go ahead and try it with the newer recommended version. if the error message just says that the library can't be found anymore, go ahead and take it out. And the reason for that is that as I was compiling these compilation from source OpenCV instructions, if a utility seemed to be most likely necessary, I included it. As a result of that, some of these utilities are essential, whereas to be honest, some are not. So if you're doing this a year from now and you get an error and a newer version of something isn't suggested, you can just take it out because it probably isn't essential, to be honest. A little bit of research may be involved in some cases if concerns are still experienced during the compile because one of these was taken out and then OpenCV won't compile. I hope that won't happen for anybody, but I can't promise it because, again, I cannot guarantee what will or won't happen with any of these software utilities going down the road. But at least for now, this will work. So bearing in mind what I've said so far, let's go ahead and run it. And you'll see that many of these are already installed to the latest version. So we can go ahead and continue. Okay, so our various utility programs have successfully installed. Now we're going to use the wget command to download OpenCV 3 from SourceForge. And if a later version than OpenCV 3.0.0 is available as of when you're watching this video, of course you're welcome to go ahead and try the latest version. I don't anticipate any major changes in OpenCV 3 immediately. Okay, so wget just completed, so now we're going to go ahead and unzip OpenCV, and this will take a moment since OpenCV, of course, is a very large program. Okay, so OpenCV just finished unzipping, so we're going to cd into the OpenCV 3.0.0 directory, and then we're going to make a directory build, and then we're going to cd into that, and then this next command here, cmake, will set up the necessary files and data for the OpenCV compile, and this takes just a minute to generate. Okay, so the cmake command just completed, so now we're ready to go ahead and do sudo make. Before we do that, as you see in the picture-in-picture, I've perched the Raspberry Pi on a small metal object and removed the top half of the case. Those are good precautions to take to prevent overheating during the sudo make command, since this does take about 3 hours and is going to have the Raspberry Pi processor going pretty much as fast as it can the whole time. So those would be good precautions to take. Once you've gone ahead and done that, we'll go ahead and do sudo make. Okay, so our OpenCV compilation is finally done, so now we're going to do sudo make install. Okay, sudo make install is complete, and now we're going to open the following file. It's set ldso.conf.d and then opencv.conf. Actually, we're creating this file because it hasn't been made yet, but we'll go ahead and execute this command with nano, and it's blank because it hasn't been made yet, so we're just going to add one line to it, and that's user local lib, and then you can either press the down arrow or the right arrow or enter to go to the next line. It's a good idea to leave a blank line there. And then do Control O to write out, and then Control X to exit. Now we're back at the command line again, so we're going to do sudo ld config, and then we're going to edit bash.bash rc as follows: sudo nano etset bash.bash rc, and then we're going to scroll to the bottom here, and then we're going to add the following two lines. There's one, and there's the other, and then leave a blank line, and then Control O to write out, Control X to exit. And as a precaution at this point, we should reboot. OpenCV might work without a reboot. Let's go ahead and do one to be on the safe side though. So sudo shutdown -r now. And of course we temporarily lose our connection there when we do the reboot. So I'm checking behind me here to see when the Raspberry Pi boots back up, so simply reload my default here, and it'll be just another moment. And what we're going to do once we can restart our session is we're going to start a Python interactive prompt session and check to make sure that, okay, that's done. We're going to check to make sure that the OpenCV install was successful. So let's go ahead and choose open here and make this a little bigger again, and log in as Pi, Raspberry. And now we're simply going to type or copy and paste, as the case is, Python. That brings up the Python interactive prompt. And now we're going to do import CV2, and as long as we don't get an error there, that's a good sign. And then we're going to do cv2.:version:, and there we go, 3.0. So the installation was successful. Python can see our OpenCV install. And so continuing on with the cheat sheet, the next thing that we're going to do is we're going to test, we just did this here, we're going to test our OpenCV install by running OpenCV test 1, 2, and 3.py. So let's go ahead and return to the GitHub site. Let's see here, my controls and more, GitHub, okay, go here. And then these are the three we're looking for here, OpenCV test1.py, and this supposes that there is a file in the same directory as the script is being ran from called image.jpg, which if you follow the camera testing instructions earlier will be there. So let's see, Control A, Control, actually we got to hold off on that for just a second. Okay, so to get out of the Python interactive prompt session, we're going to do Control D. That brings us back to the regular command line, and then we're going to do nano OpenCV test1.py, and that's going to bring up OpenCV test1.py in the nano editor, and then we're going to finish copying and pasting from where we were just a moment ago. So right click anywhere in the PuTTY window, and then Control O and Control X, and then we can go ahead and run that to make sure OpenCV works. And via X forwarding we should get a canny edge image of the picture we took earlier. So there's the original picture, there's a canny edge image, so that worked out okay. And now we're going to do a webcam test. So nano OpenCV test2.py, and I think you're going to get the idea here, but I'll just show you what I have going on my other screen here in case you're curious. So OpenCV test2.py, and then raw, and then we're going to copy and paste all that and paste it into PuTTY and give it just a second there. Okay, Control O, Control X, and this of course will test that webcam works, and via X forwarding should bring up some windows here, and I'm going to go wave my hand in front of the camera for just a second to prove that it's live footage. Just another moment. Okay, there we go. You can see that there is a huge time delay because of the X forwarding, but it clearly works. So let's go ahead and exit out, and again because of the X forwarding there's even delay exiting the program. I think if we go to the command line and do Control C, that should do it. There we go, finally exited. And then we'll test our red ball tracker program. This will not pan and tilt servos yet, we'll get to that later, but let's do the just still image red ball tracker first. That's OpenCV test3.py, and copy and paste out a raw and paste into there. And once that pastes in, there we go, Control O and Control X, and then we're going to run it, Python OpenCV 3 test.py, and I'm going to go grab a red ball and hold it in front of the camera. And what you'll want to do is watch the command line to see the location of the ball being shown. Because of the X forwarding lag, looking at the windows isn't going to be especially helpful. Okay, so there we are. The X and Y position of the ball and the radius are clearly reported, so the ball is successfully being detected. Again, because of the huge X forwarding lag, we're not really able to see that in the windows. Adjusting my microphone a little bit there, but that's okay. We can exit out of the program now and do a Control C from the command line and do the X forwarding lag. It's going to take a moment to exit the program, but that's okay. So continuing on with the cheat sheet. Now we're to the example servo motor control program. Okay, so continuing on to the servo motor control section. First, for just a moment, we're going to actually revisit the circuit we used in the LED blinking program. So let's return to the GitHub site here. Okay, so earlier what we did was we breadboarded myblink.png and then ran myblink.py. So now we're going to, instead of blinking the LED, we're going to control it with pulse width modulation, and then we'll control the servo with pulse width modulation. But let's start with the LED just so it's a little more straightforward to begin with. So we have this circuit here, LED pwm.png, and this actually is the same circuit as the LED blinking circuit that we did earlier. So you can go ahead and re-breadboard that circuit or just use it how it is if you kept it breadboarded. And then we're going to run this led underscore pwm.py file here. So first we have to create it here. Okay, so we're going to sort of pick up here. So cd to the home directory if we're not there already, or actually we already were, but just to make sure. So then we're going to make the file touch led underscore pwm.py, and then we're going to open it for editing, and then we're going to copy and paste led underscore pwm.py into there, and give that just a second. Control O and Control X, and now we're going to go ahead and run that, and sudo python led underscore pwm.py. And so what this program does here is, by default the brightness is 50%, and then the brightness is controlled with pulse width modulation. So if we enter a 0, that'll turn it off. If we enter a 100, that'll turn it to full bright. 50 is half bright, 75 is 3/4 bright, 25 is 1/4 bright, there's 50 again, there's 100 again. You get the idea. So we've got pulse width modulation working for us. So just to take a quick look at that, open it here in Nano again. So what we do is we do the set mode. That's the same as in the Blink program, and then we assign our number 18, our pin, I should say our GPIO pin number, to a variable, and then we use the setup function to set that pin to be an output pin, because we're using that to high side drive the LED. So this is just the same as in the LED Blink program. Here it gets a little different. We're going to call this function gpio.pwm, and then we're going to pass in the LED GPIO pin and then also 500. And what that frequency is that's the frequency in hertz. And then we're going to and that this function here, gpio.pwm, returns this pulse width modulation object. And then so next we're going to call the start method on that, or start function, to set the initial duty cycle to 50%. And then we're going to enter our infinite loop, and then we're going to, from the keyboard as you saw, we're going to call the raw input function to get the requested duty cycle as a string. Then we convert it here to an integer, and then we call pwm object.change duty cycle, and then we pass in the updated duty cycle, and that updates it. So that's how we can perform pulse width modulation with the Raspberry Pi. The Raspberry Pi is not a real-time operating system, so for something precise such as controlling a servo motor, you are going to get a little bit of servo jitter, but it does work as far as at least basic servo motor control, as we're going to see shortly. So let's exit out of that now that we've gotten that running. So the next thing that we're going to do is we're going to breadboard another circuit here. Okay, so the next thing that we're going to do is we're going to breadboard simple servo.png, and then after that the next circuit that we're going to breadboard is going to be pan and tilt tracker.png. So looking at these two circuits here, here's simple servo.png, and that's not really big enough here. Okay, there we go. So here what we have, this is a pretty straightforward LM317 power supply, and this here is our input. That's 9 volts. Well, I have it labeled 9 volts here. Really, this could be the LM317 is going to have a dropout of maybe as high as 2 volts. So basically this here has to be at least 7 volts. Other than that, it can be pretty much anything. So you could use a 9-volt battery, you could use a wall-wart 7 or 9 volt or even 12-volt power supply. Basically you wouldn't want to go with something extremely high here like 30-some volts, because the heat dissipation of the 317 wouldn't be enough. It would overheat then. But as long as this is anything remotely close, so I'm just going to use a simple 9-volt battery today. And what this arrangement is going to do is give us a regulated 5.9 volt output here to power the servo motor. So we're going to apply that over here, and then of course we ground the servo motor, ground the Raspberry Pi's ground pin. You can pick any of the pins on the right side of the Raspberry Pi to ground it. I just pick 30 here because it fits with the next schematic, which we'll get to in a moment. And then the control pin of the servo, which is these are usually with servos, they're either yellow or white, and that goes to the Raspberry Pi GPIO pin. So in this case GPIO 24, which is physical pin 18. And it's a good idea, the Raspberry Pi the pins can be a little sensitive to over voltage or over current, so it's a good idea to put a resistor in here just in case the servo does anything unusual. So this circuit here is simpleservo.py, or simpleservo.png rather, which goes with simpleservo.py, but I'll kind of mention this now just to save you some time, is that the next circuit, pan and tilt tracker.png, this circuit includes everything that was in the previous circuit. The power supply setup on the left is exactly the same, and the connection off of physical pin 18 is exactly the same. The only difference here is we have an additional servo on pin 22, and then we also have a LED. So if you want to save yourself some time, you can just breadboard this circuit to begin with. That way you don't have to do simpleservo.png and then pan and tilt tracker.png as two separate circuits. So I'll just go ahead and breadboard this one to begin with. Okay, so here we are. We've completed breadboarding our pan and tilt servo circuit, and we can use this, of course, for both the simple servo test program and then the pan and tilt program at the end. So you can just go ahead and breadboard it this way to save yourself some time. And so here we've got our pan and tilt kit and our webcam all set up. And if you're wondering where I got these specific servos and then the pan and tilt kit and these nice brackets, I got them all from Servo City. They're in the parts list. And then so this area of the board here is our power supply, of course, and then these here are the connections for the pan and tilt servo. And then here's our Raspberry Pi, of course, over here, and here's the LED that we're going to use eventually to tell if we're successfully tracking the ball or not. So let's head back to the desktop. Okay, so we've gone ahead and breadboarded this circuit now. So let's see, continuing along with the cheat sheet. Let's see, next breadboard simple servo, then create the program. Okay, so we left off here. So let's bring back up our PuTTY session here. So we're going to make simpleservo.py, and then we're going to go back here and we're going to go to simpleservo.py and then raw and then copy and paste. And this program is actually very similar to the last one. Really, the only difference is that we're controlling a servo. Well, let's get it working first, then we'll take a look at it. So we'll paste it in, Control O to write out, Control X to exit, and we'll go ahead and test. So sudo python simpleservo.py, and there's that servo jitter I was referring to earlier. You can, I think, both see, and I'm not sure how well this captures on the microphone of the webcam, but hopefully you can also hear that the servo's jittering just slightly. Of course, it should be pointed perfectly straight at 90 degrees at this point, but anyhow, let's go ahead and test. So if we enter our desired angle of 0, there we go to 0. If we enter 180, there we go to 180. We can go back to 90. We can go to 45. We can go to 135. We can go back to 90. We can go back to 180. We can go back to 0. So again, it's not perfectly accurate because of the timing of the Raspberry Pi. The Raspberry Pi being that it's running a full operating system, it has to do other things in the background and can't guarantee perfect servo timing, but you can see it works pretty well. So we'll exit out, and let me pause for just a second here. And before we continue on to the pan and tilt tracker, using the servos to make the camera move to track the ball, let's first take a quick look at simpleservo.py now that we've proved out that it's working. So the beginning here is essentially the same as the previous program where we pulse width modulated the LED, the only difference being that we're setting our initial frequency to 100 Hertz and our initial duty cycle to 14%, and again I'll explain how we came up with that in a minute. This is pretty much the same. We just get the number from the command line, convert it from a string to an integer, and then this line, of course, was not in the previous program. This is where we tried to determine the duty cycle for the servo, and we do that with this formula here where we pass in the angle to it. And again, I'll explain this in just a moment, but once we have the duty cycle, then we simply pass it in to change duty cycle, just as we did when we were pulse width modulating the LED. So to explain this calculation, let's take a quick look at that. So the first thing you're going to want to do to determine servo calculation is you're going to want to take a look at the timing for your particular servo. So if we go to the parts list, and the servo that I'm using here just as an example is this Hi-Tech HS 645MG. So if we bring up pretty much any data source for that, and let's see, I believe Servo City comes up pretty quickly. Yes, there it is. And if we look down here, we'll see that to go to the leftmost position, you need 600 microseconds on time, and to go to the rightmost position, you need 2400 microseconds on time. And then, of course, that's essentially proportional across, maybe not absolutely perfectly proportional, but effectively it's proportional across. So what does that mean as far as servo timing? Well, I made this timing diagram here to explain that further, and here we go. Example servo timing calculation.pdf, and then let's do raw, save it to the desktop. Okay, so I paused for just a second there to turn off the picture-in-picture and completed the example servo timing calculation download here. So let's go ahead and take a look at this document. So when controlling servo motors, we can generally adjust frequency or period and duty cycle to set the servo angle. So recall our basic formulas here relating period and frequency. Period equals 1 over frequency, or in other words, frequency equals 1 over period. So next we should look up the timing for our specific servo. So for example, the Hi-Tech HS645, we just looked on this website here, and then we found that a 0-degree angle required a pulse of 600 microseconds on time, or 0.6 milliseconds, and a 180-degree angle required a 2400 microsecond or 2.4 milliseconds on time pulse. So in other words, to achieve a spread of 180-degree movement, so going from 0 to 180 degrees, we needed to achieve a spread in pulse time of 2.4 milliseconds minus 0.6, or a total spread of 1.8 milliseconds. Now note, you don't start at 0 milliseconds to get 0 degrees. There's an offset. You have to start at 0.6 milliseconds to get 0 degrees. We'll come back to that in a moment though. So in other words, we essentially could build this table here if we go from a pulse time of 0.6 milliseconds gives us a 0-degree angle, and then through these increments up to 2.4 milliseconds gives us a 180-degree angle. And with most servos, including the Hi-Tech HS645MG, this is a pretty standard servo. With most servos, if we send a pulse at least every 20 milliseconds, that's sufficient to maintain the servo position. So to be on the safe side, we'll send a pulse every 10 milliseconds. So in other words, we need a period of 10 milliseconds, or 0.01 seconds, which, if we refer into the formulas above relating frequency and period, we can do 1 divided by 0.01 seconds equals 100 hertz is the frequency that we need. So that's where we got this number here in code. Frequency is 100 hertz. Okay, so continuing on, here's just what an example period would look like for if we were trying to command a 90-degree angle. So as we discerned up here, if we have a pulse of on time of 1.5 milliseconds, that should give us a 90-degree angle. So out of our 10 millisecond period, we'd like to be high for 1.5 milliseconds and then low for 8.5 milliseconds. And so the next thing that we have to do is we have to calculate how much on time do we need per degree, and that breaks down pretty simply here. So we have a spread of 1.8 milliseconds that we need to cover our 180-degree angle spread. So if we do 1.8 milliseconds divided by 180 degrees, that tells us that we have to add 0.01 milliseconds of on time per additional degree of servo angle we would like to command. So we'll find that we can drop the numbers essentially into this formula here. So we have the desired angle we'd like to achieve, so that's anything from 0 to 180. And if we multiply that by our millisecond per degree number from here, and then we need to add the offset in milliseconds to get 0 degrees, and then we multiply that by the period in milliseconds, that will give us the duty cycle in percentage. So for this specific servo, for example, we're going to have desired angle, which again, that was what the user input from the command line. So referring back to code here, so we're actually asking for the desired angle 0 to 180 degrees, and then that gets fed into the formula here. So that's effectively the input to the formula, and duty cycle is the output. So if we do desired angle times our 0.01 milliseconds per degrees plus our 0.6 milliseconds to achieve 0 degrees, that's our offset, and then we multiply by our 10 millisecond period, that gives us our duty cycle in percentage. So for this particular servo, for example, here's what we could use in Python. And with servo motors, every time you do this calculation, this is really a starting point. Don't think of this as a finish. So what I found out from experimentation is that tended to make the servo rotate from about -5 degrees to 175 degrees. So I had to just experimentally determine that this offset angle, if I used 0.5 instead of 0.6, actually worked out a lot more accurately. And this gave pretty accurate results. So you're going to find, depending on your particular servo, you may have to tinker with the formula a little bit once you calculate the ideal to get to the practically working formula for your hardware. So that explains how we achieve this formula, and we can use this formula again in the next program when we're panning and tilting the camera to track a red ball. So let's go ahead and take a look at that. Okay, so we've already breadboarded pan and tilt tracker.png, so let's go ahead and we can exit out of simple servo, and then we need to make pan and tilt tracker.py, so nano pan and tilt tracker.py, and let's see, we can close out of the servo timing document there, and we don't need this anymore, so let's go here, and then we can go to pan and tilt tracker.py, and then let's take a quick look at the raw code. And let's see, well actually let's copy and paste it in first, so Control A, Control C, and then we can copy and paste it in here. And so taking a quick look at this, just another moment here while it copies and pastes. Sometimes there's a little bit of lag copying and pasting a larger document into PuTTY, and there we go. So most of this code is pretty self-explanatory. You can either run the application headed or headless, so of course if it's headed then you're going to get the two windows that show the original image and then also the processed image. And another change from the previous programs, actually the same as the previous webcam programs, but it's worth mentioning. In this part here what we do is we change the resolution from the default to 320 by 240. You may want to try leaving it as the default, especially with many webcams that'll be 640 by 480, and you may actually find you get better results, especially if you're running it headless. The Raspberry Pi can, generally speaking, still do computer vision at 640 by 480. There will be a little bit of a lag, so you can't move the ball too quick, but it will detect it at more of a distance. So let's go ahead and write out, and then we'll exit out of there. And then so let's first test in headed mode. Actually, let's first test in headless mode. So just a second here. So I'm going to start it up and then go ahead and put my headset down and move the ball in front of the camera a little bit. Okay, so that's a little bit crude, but you can at least get an idea that it works. So let's go ahead and cut that off, and actually let's try commenting out the resolution change. So this is going to go to 640 by 480 resolution. So let's see if we comment out this line. Actually, let's leave the resolution display there. We'll just comment out changing it. So write out and then exit, and let's run it again. Okay, so you can see that's rather crude. Let's cut that off once and then do another quick test with the camcorder. Okay, so now we're testing from our webcam, and again you can see this is lighting dependent and somewhat crude, but it does work. Now obviously there's a ton of potential improvements that you could make to this setup to improve performance, but at least for something to start with, this will work. Okay, so here we are back at the separate keyboard and monitor for the Raspberry Pi. And here we can take a look at the windows in headed mode, so you can actually see the ball being tracked. This is maybe a little bit more helpful. And you can see the tracking it's certainly not perfect, plenty of room for improvement, but at least for something basic to start with, it is a working version. Okay, so we've completed the Raspberry Pi and OpenCV Part 1 tutorial, and we started from the very beginning with the Raspberry Pi and went all the way through operating the Raspberry Pi from a Windows desktop with PuTTY and Xming, getting a LED blinking, compiling OpenCV from source, controlling hardware, and then a final project that combined OpenCV and hardware control. and hopefully some people out there who are either getting started with the Raspberry Pi altogether or who are using OpenCV on the Raspberry Pi for the first time will find this beneficial. You may have noticed I titled this Part 1. I may do a Part 2 and possibly even a Part 3 with the Raspberry Pi and OpenCV, depending on how well received this video is. If you found this video helpful, please consider supporting me on Patreon, and please rate, comment, and subscribe, and I'll see everybody in the next one.